Time passes so quickly, yet time lasts forever. Our 80 years and 10 merge with those of past generations and into history. In Orkney and Caithness, we have a strong sense of that. The family histories of flets and firths that go back to the Vikings, the ancient homes at Scaraben and the stone circles at Stennis that take us back to the earliest pyramids. But geological time, it's so immense that it seems like stepping into infinity, millions upon millions of years. In this film, we open a window on deep time. We ask, how old are the hills?
Hello.
Mara, it's great to see you again.
So good to see you too.
So we're off on another trip.
I know, quite the ambitious venture ahead of us.
Yeah, this is a big one, a very ambitious one. We're going to try and have a look at geological time.
Okay. How are we going to do that? Because we can't see time, so how on earth are we going to make a movie about it?
Well, perhaps we can use the rocks to help us understand a little bit about the span of time.
Okay. Another point then, what about the numbers? Talking about geological time, that's some big numbers. Hundreds we can understand, thousands, okay, but we're talking millions of years here.
Oh yeah, well, yeah, millions are very difficult to grasp.
Yeah.
But perhaps what we need to do is to split up millions of years into manageable chapters, into manageable time spans.
Okay. We only have 45 minutes.
Oh, well, sure, but you know, the maths on that is that we've got to cover about 100 million years every minute.
Okay. We better get a move on.
We better have.
Let's go.
So, Mara, we've come to time span where they have this rather remarkable geology garden with these huge boulders. And the boulders represent the main rocks of the Northern Highlands.
Okay.
We've got some of the oldest rocks. So this one is the Lewisian gneiss.
Okay.
And that has an age of up to 3 billion years old.
Wow.
So it's either some of the oldest rocks on Earth, never mind Scotland.
Gosh.
So this is at the bottom of the rock pile.
Okay.
And then over here we've got the Caledonian sandstone, which you find in the Northwest Highlands.
Okay.
That's about 1,000 million years old.
Wow.
And these are an example of the Moyne schists. The Moyne is called, it has its name because it dominates the peatlands of Sutherland, the Moyne. So these are about similar age.
Okay.
And then we come to the Helmsdale granite, this thing here.
Helmsdale granite.
Yeah. So this is the granite that forms the hill behind Helmsdale.
Wow.
It's about 440 million years old.
Okay.
Intruded deep below the Earth's surface, maybe 5 kilometers under the ground, and solidifying. And then after that solidified, we had mountains and we had erosion, and that gave us that gravel rock in the background.
Oh, okay.
And we'll see some more of these conglomerates properly later.
Okay.
So that basically is the rock sequence for this part of the silence. And it's really interesting.
So it's very interesting to you. To me, it's lots of big rocks with some different colours and some different textures, and that's fine. But it's the hills that are far more interesting to me. That's where I go exploring.
Okay.
That's a movie.
So we need to be able to visualize long periods of time.
Yeah.
So we need a timeline.
Okay, I see you've set one up here.
We've got one here, and we've got a meter rule.
Okay.
So on that time scale, we can say, let's have a millimetre equal a year.
All right.
So that's 1,000 years.
Okay, we've got St Mary's Cathedral in about 1136.
That's right, that's
Okay.
when they started building it.
Excellent.
And here we have a broch.
It's a low budget film after all.
It is. And then as we move to around 4,000 years ago, we've got Scaraben.
Another very accurate representation there.
Thank you. Off to Egypt and the pyramids at about 5,000. And then we march through time back to 10,000, and that's the end of the Ice Age, and that's the last of the mammoths as well.
All right. But where do we go from here?
Well, we've got a long way to go, haven't we,
Yeah.
in terms of time?
Why don't we start by heading along the A9?
Well, it is the longest road in Scotland. Let's see where it takes us.
Good place to start.
So, on our A9 timeline, how far does that take us?
So if we talk 1,000,000 years, that's a kilometre. That barely gets us outside of Helmsdale.
Yeah, it also means that we're still in the Ice Age, right at the middle of the Ice Age.
Yes.
However, if we go a bit further, for example, if we go down to Inverness, that takes us back to about 65 million years. That's the end of the Cretaceous period and the end of the dinosaurs.
Oh.
And if we get down to the English border at Carlisle, leaving behind the A9, then we're more or less equivalent in age to the Helmsdale granite behind us.
Wow, okay.
About 400 million. Continuing on, if we go all the way through England and down to Land's End, that's at about 1,000 million, the age of the Caledonian sandstone.
See, that's massive, but we're talking to the beginning of Earth. Surely we've still got a long way to go.
Yeah, we've got another 3,500 million years still to go.
So where on earth does that take us?
Well, by my calculations, I think that takes us to here.
To Timbuktu.
Yes.
Wow.
All the way from Helmsdale to Timbuktu.
Excellent.
On the A9 timeline. So from our magnificent vantage point here, I think the rocks and the scenery give us evidence of 3 separate mountain building periods.
Okay.
Most obvious one is the hills. The hills are the easternmost outpost of the Northern Highlands.
Okay.
So they're actively eroding today. And the Northern Highlands was uplifted from close to sea level about 60 million years ago, when the big volcanic centres on Skye and Mull became very active. And the whole landmass was tilted towards the North Sea.
Gosh.
But most of the rock underneath these peatlands is the Old Red Sandstone. And the Old Red Sandstone is Devonian age, around 400 million years old in terms of age.
Wow.
And there's a lot of it. It basically forms an area which encircles the ridge of Scaraben in front of us. So you know these hills here very well.
Yes,
So
I do.
What have we
So
got?
just to the right of Scaraben, we have got Smean. In front here, we have Maiden's Pap, and then just tucked in behind it there, we have the Morven.
Yeah, they're very distinctive hills, are they not?
Very.
Yeah. So this Old Red Sandstone is itself the waste of the Caledonian mountain building period.
Okay.
So we had a mountain building period where we generated mountains which were bigger than the Himalaya are today.
That's incredible to think about.
Well, it's maybe 10 kilometers high. Really, really big mountain ranges. But Scaraben is made out of quartzite, and that's a metamorphic rock. But originally it was a quartz sandstone. So that sand came from a yet earlier set of mountains. And the Scaraben quartzite is something like 840 million years old. So that gives us 3 separate periods of mountain formation.
Yeah.
And these rocks, they show us, they tell us a little bit about the middle one of those periods, the Caledonian mountain periods. So we'll go and have a look at those.
Sounds good.
Okay.
So I don't remember seeing anything like this at time span. I mean, to me, this looks like scree, but compressed. It's a rock, isn't it?
Yeah, it's rock, and it's old. This is all red sandstone, but
Okay.
of course it's not red.
No.
And it's not sandstone because it's got all these bits in it. And we can see that the bits are actually quartzite. All of these rocks are basically the Scaraben quartzite.
Right, okay.
So this rock is hundreds of millions of years old.
Okay.
And it records the Caledonian mountain building period and the amount of erosion that was going on. This is not a kind of frost-shattered scree. This is probably more like the kind of debris that you would get in the Atlas Mountains today or in the edge of the deserts. And then occasionally you get really big floods and they bring down enormous amounts of debris.
Okay.
So in terms of our mountain building periods, this is the detritus of the second mountain building period, the Caledonian mountain building period.
Okay. Wow. Now, Adrian, I think I've seen rocks similar to this when I've been out hill walking on Smean.
That's a terrific hill.
It is. Shall we go and have a look?
Yeah.
Now, this is what I was talking about.
That is a spectacular lump of rock.
Isn't it just? And it does look similar to what we saw earlier.
Yes. So this is another breccia. It's got these really angular fragments. Almost all of them are quartzite.
You're saying quartzite, but this is a lot more grey than we saw before. I'm guessing that's just lichen, but there is also some dots of red I can see as well.
Okay, so we've got some grey lichen, which is the dominant one. We've got a nice little green lichen here, very beautiful.
Yeah.
But holding it all together is this red sandstone. So this is the old red sandstone, Devonian rock. And what we're looking at here is very dense flows of debris, huge volumes of debris, big boulders,
Yeah.
massive energy. So this is a mountain shedding debris.
Wow.
And being deposited here.
Gosh, it certainly is something. Now this bed of rock, it's like quite an angle. It kind of just looks like it's shooting off into the sky.
I think that's probably taking us back into the Caledonian mountains. Look at the size of some of these boulders.
It is huge. So Scaraben has just opened up in front of us here.
Amazing, because that's the Scaraben quartzite. That's the source for all this debris in this rock.
You say that though, but the bed of this is at such a steep angle. Surely that would go way above where Scaraben is.
Yeah, you're absolutely right. So those beds are going way over the top of the hill. So it was a big mountain.
A mountain?
Oh, yes.
But we're already about 500 metres up. So how high are we saying these mountains were?
Well, the Caledonian mountains, 5 kilometres would not be a problem.
That is massive. That's absolutely huge. Is there a way we can visualise this? For this? Okay.
Yes.
So if I was to open this up and we were to compare this to the skyline and the ridge of the Scaraben, do you think we could do a little comparison?
Well, you can use those beds as a guide.
Okay. So if I hold this up...
Yep, I'll need to help.
What do we think?
Not enough.
Not higher, okay. Oh, but now.
Not bad.
Not bad. I'll see if I can go a little bit higher.
Oh, okay, I think that's great.
Perfect.
We leave behind now the Caledonian mountains of 400 million years ago, and we return to the highlands of today.
Okay.
But not strictly today, because these hills first started to rise about 60 million years ago, and they've been eroded down ever since. But a tremendous view.
It's absolutely glorious. Yeah, we've got Morven over here, and then just to the right of it, we've got Graham Moor and Graham Beg.
And the great plain of Caithness.
Yep, the lowlands beyond the highlands.
Ah, yes. Now, the imprint of glacial erosion on this side of the Northern Highlands has been quite light.
Okay.
So what we're looking at here, these plains are, they were formed by rivers before the Ice Age.
Wow.
So they have quite a history.
Yeah. Fantastic.
Now let's go and have a look at some of these tours.
Let's do it.
So two of the really striking features are these little rocky hills, and we've got some excellent examples on Smean. They're usually associated with granite.
Okay.
Most famous ones, I guess, are Dartmoor in England, south of the limits of glaciation. And we tend not to find them in glaciated areas because any sliding ice will take out these very delicate forms. Right,
okay. So why are these still here?
Well, that's a good point, because they're evidence that there's been very little glacial erosion on top of these hills. We know that the ice sheet has been thick enough to cover the hills, and we have some glacial erratics on the hills, but clearly the ice was not sliding across them.
So they were pretty static then?
Yes, they were moving, but they were creeping internally, and the key thing is that they were actually frozen to the bed.
Wow, okay.
So the deformation was taking place within the ice.
Wow.
So they, in a way, were protecting the bed.
Excellent.
But we're here to see if we can pin down just how fast are these hills being eroded.
Okay.
Now, clearly, because these hills are here, they're eroding more slowly than what's around them. That's why they stick up.
Yes.
Okay. But we really want to know how fast.
Yeah.
And we have to do some really clever stuff. So these surfaces have been sampled for cosmogenic nuclides.
Wow. Okay.
Right. So, you know about cosmic radiation.
A little bit.
And we have these very complex interactions of the atmosphere. And part of that is a rain out of secondary radiation, which includes isotopic nuclides.
Okay.
So these samples contain aluminium-26, beryllium-10, and we know what the half-lives of those are. So that means we can use them as a geological clock.
Excellent, okay.
Yeah. So we know the theory of it, but the practicalities are mind-blowing, because the concentrations of these nuclides are basically the atomic scale. And I once had it explained to me that it's like looking for 2 golf balls on the surface of Australia. It's absolutely amazingly
an easy task, I'm sure.
Anyway, the guys down at East Kilbride in Glasgow at the Scottish University Research and Reactor Centre, they can do that kind of analysis.
Wow.
And so we know how many cosmogenic nuclides there are in here, and from that you can work out the rate of erosion.
Okay, so what is the rate of erosion?
Drum roll. The rate of erosion is 3 meters per million years.
Okay, to the non-geologist, is that fast or slow? What does that mean?
That's very, very slow.
Okay, why is that?
Well, partly because the rock is made out of quartzite, which is silicon dioxide, same composition as glass, so chemically very inert.
Okay.
And partly also because the rock is really well stuck together and cemented.
Ah, okay.
So it's really hard for weathering to do work. We can kind of see that because there's not much debris around this little rock face. It's not as crumbly as it looks.
It's all
really
pretty intact.
Rigid, yeah. So it is eroding very slowly. But actually, this is one of the oldest rock surfaces that we know of in the British Isles.
Wow, that's impressive.
So Mara, we're now down at Berrydale.
Yes, we are.
At the mouth of the Langwell Water and the Berrydale Water.
Absolutely.
And those rivers, of course, bring down from their catchments all the rocks that sit within them.
Yes. So we've got some Scaraben quartz here.
Yep.
We've got some Helmsdale granite. And what have you got beside you?
Loads of old red sandstone.
Okay. And why have you had us rock hunting? Why have we built these towers? What does it represent?
Well, when we were at Helmsdale and Smean, we identified basically 3 periods of mountain building. We identified an ancient period, which led to the deposition of the sand in the Scaraben's quartzite.
Yeah.
And then we had the Caledonian mountain building period, when the Helmsdale granite was intruded. And then we've got the present highland mountain building period,
right, okay.
Which started 60 million years ago. So it seems appropriate to have the right rocks in the right places.
Yes, it does.
But this whole business of mountain building and erosion is quite tricky because we've got to place it in time, and we've got to get a grasp of the rates of mountain building and also the rates of erosion.
Okay.
So we have no mountains left from our first mountain building period.
No.
It's the Scaraben quartzite just represents the waste, the sand that came off those mountains.
Okay.
And then they were really deeply buried. They were metamorphosed, so the quartz grains were fused into really hard rock.
Okay.
Those mountains were effectively eroded away.
So I can maybe take a few of these off then.
And the amount of erosion, as we saw yesterday, is kilometre scale. So 2 pebbles doesn't
really represent it. Okay.
Anyway, we get rid of the ancient mountains, but then at about 440 million years, we've got granite intrusion 5 kilometres below the surface, uplift, and within a few million years, that granite is at the surface.
Okay.
And we know that because the granite is present in the old red sandstone conglomerates.
Yeah.
So we're eroding this.
Okay.
And the debris is ending up in the conglomerates.
Right.
Here.
Okay.
We then have the erosion of all that Devonian sandstone and cover.
Okay.
to get close to where we are today.
Yeah.
But 60 million years ago, in the west, we had volcanic activity and the highlands were pushed up.
Okay.
So this represents the most recent mountain building period that created the highlands.
Wow.
So what we've effectively got here is 1,000 million years of Earth history, very simply summarized.
All on one bit of rock?
Yes.
Excellent.
Not bad for a morning's work. So down at Berriedale, it's probably appropriate that we acknowledge that we're not the first people to look at deep time in the county of Caithness.
Or not?
This book was written 50 years ago by Donald Olmond from Halkirk, and it is remarkable in the way that it deals with time.
Okay.
Donald starts way back in the Louisian gneiss, as old as you can get in the rocks, comes all the way through to the Ice Age, and then starts delving into historic time and even the more recent changes in the farming industry and the fishing industry. It is quite remarkable.
Now, Adrian, I want to bring us back to our piles of rocks, our mountains, sorry.
Yes.
You know, how old are the hills? We've discussed some big numbers, but, you know, how quickly did these uplift and then erode?
Well, that takes us into considering rates of geological change, and it means that we have to introduce this fellow.
Okay.
This is Sergius von Bubnov.
A very dapper-looking gentleman.
Yes, Sergius was a geologist who operated out of St. Petersburg in the early part of the 20th century. And he was interested in standardizing rates of geological change.
Okay.
And he came up with a unit which then took on his name. It was the Bubnov.
Excellent.
So let's take a look at the Bubnov unit. A meter in a million years.
Okay, so that would be a micron per year then.
Uh-huh.
Okay.
And that, of course, is incredibly slow.
Yes.
But if we go for kilobubnovs, then a kilobubnov would be a kilometer in a million years.
Okay, or a millimeter per year.
Yes,
Yeah.
and that's, I think, more like the normal rates of change in the landscape.
Oh, wow.
So let's apply the Bubnov rate to the hills we've seen at Helmsdale and at Smean.
Okay, I think that'd be useful.
I brought along a rather special device here.
Okay, it looks a bit like a wee tablet to me.
I call it the Bubnometer.
Okay.
It's a demystifying approximator of deep geological time.
Fancy.
Well, it'll help us visualize, I think, some of the rates of geological change.
Okay.
So for the Helmsdale granite, this was basically intruded at a rate of 3 kilobubnovs.
Okay, so that's 3 kilometers per million years.
Yeah.
Got you.
And then the debris that was eroded off the top of the granite and ended up in the Devonian conglomerates, the old red sandstone, that was deposited at about 1 kilobubnov.
Okay, so 1 kilometer per million years.
Yeah.
So a bit slower.
Yes, but still quite fast
Yeah.
in geological terms. And if we jump forward in time to the Ice Age, then on Smean we were looking at tors which were eroding at 3 bubnovs.
So the 3 meters per million years.
Yeah, so that's 1,000 times slower than some of these other processes deeper in geological time.
That's quite spectacular.
Yeah, but it's giving us a handle now on different rates of geological change over different time periods.
Absolutely.
So that's useful.
Yes. Okay, so we've left Berriedale behind now, and we've come out to Dunnet Bay, my home place, and we have a new timeline in front of us here.
Yes, a very different one. This is a million-year timeline.
Okay.
This is the Ice Age timeline.
Right.
And we've greatly simplified it, of course, but what we're trying to show here is we go from today to a million years ago.
Right.
And we've got some red triangles, which are the periods of warmth.
Yes.
And the blue are the periods of extreme cold. And so these are the interglacial periods, and the blue are the glacial periods.
Okay.
This is when we get the glaciers and the ice sheets coming over Scotland.
All right, and what about the little blue triangles then?
The little blue triangles are periods when it wasn't quite so cold, the ice sheets were smaller,
Okay.
we had glaciers in the mountains.
Right. And then this cycle repeats?
Yeah, I mean, more or less, the last time it was as warm as this was 125,000 years ago.
Okay.
That's the last interglacial. And then these periods are basically spaced at about 100,000 years. And the big ice sheets also are spaced approximately at 100,000 years.
Okay. What happens to the sea level then during all of this?
Well, in the present interglacial now, we've got sea level where it is.
Yes.
Here at the beach. And the last time that happened was during the last interglacial.
That makes sense.
During the cold stages, the ice in the ice sheets has to come from somewhere.
Yeah.
So that's from snow, and the snow ultimately comes from evaporation of the oceans. So the sea level drops by about 100 meters when the big ice sheets are around, and then perhaps by 50 meters when the small glaciers are
Wow.
around.
Okay.
And that cycle repeats all the way back in time through the Ice Age. Now, as far as our visit here to the dunes is concerned, we are right at the start of this timescale. We're in the present interglacial, and we're in the last few thousand years of geological time.
Okay. Now, Adrian, I grew up here. I've seen a lot of change on the sands and in the dunes especially. I mean, after big storms in winter, you can see peat that is the kind of the underbed of the dunes. So these must be really young hills then.
Yeah, these are definitely the youngest hills that we're going to look at. Very, very dynamic features. We know that in winter storms you can have huge changes in the shape of the dunes. Mm-hmm. And the dunes haven't been around for very long. The dune system probably has only existed for about 6,000 years.
Wow, okay, that's very short, especially considering all the other hills we've discussed.
Yeah, and of course all the sand comes off the beach, so the dune is fed by the beach at present day sea level.
Okay.
If we change the sea level, then the dune is immediately affected.
Yes.
And of course, if we follow our Ice Age timeline, if the glaciers come back, the ice sheets come back, these very fragile sand hills, as the Americans call them, they're gone.
Wiped away.
Yeah, they're just wiped out.
So what does the bibnometer tell us about the rate of change of these sand dunes?
Well, it's quite interesting because your peat that you've seen, that started to accumulate about 7,600 years ago.
Okay.
And the rate of peat accumulation is 310 bubnops.
Okay, so that would be 310 meters per million years, but the million years isn't relevant. It's not been a million years. That's too long. So we could put that into 310 millimeters per 1,000 years.
Yeah,
that would be more relevant.
The 1,000-year timescale is definitely the one.
Okay.
And then when we look at the sand deposition, that's about 1,000 millimeters
per 1,000 years.
per 1,000 years.
Got you.
So that's 1 kilobubnov.
Yeah.
And the rate of soil formation is about the same, about a meter in 1,000 years.
Okay.
So These are very young features, these hills, a very dynamic environment.
Yeah, especially compared to what we were seeing on the top of Smean.
Yes, and this is a very transient and short-lived hill.
Wow.
As far as geological time is concerned.
Okay. So your journey continues.
Yes, I'm off to Orkney. I'm off to see Katie. We're going to visit a few more hills. But we'll meet up again in Kirkwall at St Magnus in a few days' time.
Excellent. I'll see you there.
Look forward to that. It's great to see you.
Good to see you again.
Well, we're just in from Caithness.
Yes, what did you get up to in Caithness with Mara?
Well, we were asking how old are the hills in Caithness.
Well, this year's a great year to be asking how old the hills are.
It is. It's nearly 300 years to the birth of James Hutton, the father of modern geology.
Yeah, quite a guy.
Quite a guy. Really the first person to understand the dynamism of the rock cycle. But it's really tricky because, of course, when you go far back in time, you're dealing with huge spans of time. And there's a famous quote from John Playfair in 1782. "We grow giddy staring into the abyss of time."
Yeah.
We certainly did get a bit giddy in Caithness.
So I brought you here, Adrian, because we're sitting right on top of some of Orkney's oldest rocks, the beautiful Stromness granite.
Oh yes, I'll have to have a look at that. Well, it's a fine example, and this one has a date on it. This is 430 million years old.
Wow. Well, how do you know that?
Well, often with these old rocks, what you use are radiometric clocks. So we use isotopes, which are in the minerals in the rock, and this one's been dated by uranium lead. So uranium isotopes, they decay to lead isotopes, and if you know the half-life of the isotope, you can figure out how old the rock is.
That's handy.
Well, this one's, it's an old rock. This is basically from the Caledonian mountain building period, so during or before the Devonian, and it's a granite.
So it was formed underground?
Deep underground from magma, and that solidified under the ground as it cooled. But of course, that could be down at depths of 5 kilometres or more below the ground. So we've got to do quite a lot of erosion to bring it to the surface.
Yeah.
But what I like about where you brought me is this
we've got
amazing wall.
Almost a model of Orkney's geological stratigraphy. We've got the granite at the bottom.
The basement.
And then this can be the sort of rubble underneath the old red sandstone layers above. So
and then you've got these beautifully stratified flagstones, which are rather like the Devonian sandstone.
Yeah.
It's a really neat physical model.
It is. It's the oldest saga in Stromness.
Very good.
So Adrian, I've brought you here because this is a place that lots of people miss if they're walking along the path. We're just below Link's Battery, and here we've got another great lump of Stromness granite from Brinkie's Brae, but we've also got something else. We've got a conglomerate, which is a bit like Rocky Road. It's got chunks of rock held together by sand, and this granite, you said before, is 430 million years
Yes,
old.
and we know that the conglomerate was formed at about 390 million years.
So this place here where I've got my finger, that's a gap of 40 million years?
Yep. So we've got basically a period of very, very deep erosion in that time. So after the granite has solidified and you've had the mountains develop, we've got to erode off the top of the mountains, any other sedimentary or igneous rocks on top, and then we've got to erode down into the granite itself before we get to this surface, which was exposed at 390 million years. So when we have this kind of major discontinuity, we call it an unconformity. And this is certainly a great unconformity because there is such a huge time gap.
Yeah. It's hard to believe it's such a huge amount of time, 40 million years, but yet today the rocks are touching.
Indeed. So when we look at the bubnometer, we get some idea of the rates of erosion and geological processes. So at Brinkie's Brae, the granite is intruded probably at a rate of about 3 kilobubnovs, which is coming up through the crust about 3 kilometers every million years. And then the deep erosion that we saw at the unconformity, that probably operates at about 1 kilobubnov, which is 1 kilometer in a million years. That's the rate at which the mountains are being lowered.
And then we started to see it be covered up again.
Yeah, so it's buried by the Old Red Sandstone. And we've got the Old Red Sandstone here that goes round to Yesnaby, and we've got the great pile of Old Red Sandstone on Hoy. And that burial by sand is probably running at about 1 kilobubnov, 1 kilometer a million years. And there's something else, because we're on the shore, and we've got this shore platform. The tide is coming in fact it's really quite close to high tide, but if we were here at low tide, this goes out for about 60 meters. The sea level has been at this level for about 4,000 years. So if we put that into the bubnometer, we actually have a rate of erosion of the cliffs here at about 15 kilobubnovs.
Wow.
Well, that's about 15 meters 1,000 years.
That's some speed.
It is fast, and that means that we're getting a grasp of the different rates of processes that operate at the Earth's surface.
Yeah.
That's kind of cool.
It's a great machine. So we're here on the southeast coast of Shapinsay at Caithness, but we may as well be in Iceland.
Yeah, there's all this volcanic rock here. We've got some volcanic vents, the feeder tubes of small volcanoes, and we've got lava flows.
Yeah, I'm sitting on the blocky top of the lava flow.
Yep. And then underneath we've got these big holes, and the holes were the gas bubbles which were released as the basalt was cooling. I can see these flow structures in the lava here, really rather beautiful. And, well, come down and have a look at this.
So these holes here, Adrian, look like they've been filled with minerals of some kind.
Yes, I think so. And that would have happened after the lava had solidified and actually after it was buried, because this happens at some considerable depth. And there's some really beautiful rocks around here.
Yeah, we found some lying around, didn't we, on our way in?
Yes. And when we look at the bubnometer, we can see the ages of these rocks. We have all red sandstone below the lava flow, which dates from about 390 million years. The lava flow itself is about 2 million years younger. And then on top, we've got the edimals.
Up here behind us.
And they date from about 385 million years. Now, they are today still 700 meters thick, and there would have been sandstone on top of those as well. And John Brown worked out that the rate of deposition of the sediment was approximately 100 meters in a million years. So that's 100 bubnovs.
Yes, and Ted Kellock also did work here. He mapped this area. It's quite complicated with faults disrupting the lava flows, and he took samples when he was visiting and he made thin sections of those samples, which we have in Stromness Museum. In his microscope slides, Ted Kellock captured moments in geological time on extremely thin slices of rock, only 30 microns thick. His slides from Caithness show gas bubbles filled by minerals. The large calcite and zeolite crystals filling the vesicles formed long after the lava cooled, perhaps many hundreds of meters underground when the lava was buried under the old red sandstone. We're on the north coast at Wieland, and we're here to look at another hill, Adrian.
Yes, this is a young hill, a glacial hill, a drumlin.
And what's a drumlin again?
Well, a drumlin is a hill made out of boulder clay, which has been shaped by the flow of ice, and typically it has an egg shape.
So it could also be a whale shape, maybe, like
Yes.
one of George Mackay Brown's sleeping whales
Oh, yes.
by the oceans of time.
That's a beautiful illusion, thank you.
And in front of me, we've got an Orkney flag-coloured timeline. Did you bring this to help us find out about the age of this hill?
Well, we've seen this before. This is a 1 million year timeline. It's the Ice Age timeline, and yes, it's just here to illustrate how young this hill actually is. Mm-hmm. And when we were at Dunnet Bay at the Sandhills, they were in the present warm period. This is a glacial hill, and it's the last glacial period, so it formed sometime around here, approximately 15,000 years ago. And of course that's very young in the context of this million years of time.
So this is the boulder clay.
Yes, there's around 10 meters of it here.
It's quite tall, and it's also, I notice, in two different colours. There's a kind of stripe.
There's a contact here between a boulder clay which is grey-brown in colour, and then a boulder clay which is strikingly red-brown in colour.
And what makes it two different colours?
Well, I think that's to do with the erosion that's going on underneath the glacier and the flow of the glacier. So here we've got the glacier crossing this grey rock,
Just like this stuff.
which is the rock that we've got here on the foreshore. So this is local rock. But in the red-brown boulder clay, we're crossing rocks which are red-brown in colour, and that would include things like the Edie sandstone.
Yeah.
And we get these rocks in the southeast of Shapinsay, so that tells us that the ice flow is from southeast to northwest. So we're getting evidence here that the ice is actively eroding the rock that it's crossing. The boulder clay represents a lot of erosion underneath the ice sheet of bedrock like this. And then after the ice has disappeared and melted, we have weathering of the boulder clay to produce a soil which has developed over the last few thousand years. And we've got erosion by the sea. And the author Stephen J. Gould described that as time's arrow, where the erosion is basically the destruction of rock and previous landforms.
But you were saying about drumlins being like egg shapes.
Yeah.
But it looks like our egg has been sliced here and about half of it's disappeared. Where's all the rest of that material gone?
Well, I suppose it's hidden from us on the floor of the bay at the moment. But that takes us to his other idea of time. Gould talked about time's cycle, and that sand and gravel which sits at the bottom of the bay may in time be transported into deeper water. It might be buried and then made into new sandstone, and those sandstones might form eventually new mountains. And that's the idea of the rock cycle, time's arrow and time cycle.
So Adrian, Mara, meet Tom Muir.
Hi, Tom. Nice to meet you.
Hi, lovely to meet you.
Lovely to meet you too.
Tom can tell us a great deal about St Magnus Cathedral.
Look forward to hearing about it.
It was founded in 1137 by Jarl Rogvald Kali Colson in honour of his uncle, St Magnus. And it was built, the middle section here was built first, but then it was extended back that way in the early 1200s, and also extended out the front as well in the early 1500s. So it's grown a bit in height and in length.
And this striking red stone?
A symbolism of martyrdom. Magnus was always portrayed as a martyr. He didn't actually die for his faith. It was a territorial dispute, but the red sandstone represents the blood of the martyr. So this is why red sandstone is used a lot in association with St. Magnus.
Wow.
And as a geologist, where's the red sandstone from?
It's from a few miles to the east of here at the place called the Head of Holland, which is just red sandstone. There's a big quarry there. The yellow sandstone came from the island of Eddy, up in the North Isles. In Orkney, we are surrounded by our history. But the Greek philosophers had two ways of looking at time. Chronos, which is the passing of time, today, yesterday, tomorrow, and kairos, the flow of time back through history. So what have you discovered on your journey through geological time?
We also found Chronos in geological time, the age of the rocks.
As fixed by the isotope clocks.
Just like we saw on the tours in Smean.
And we also found kairos, the flow of time,
So
in the layers of rocks.
So that would be on Scaraben.
As we did on Scaraben, and
Oh, and at Brinkie's Brae,
where?
in Stromness, where we have the old red sandstone lying right on top of granite, which is 40 million years older.
Wow.
The great unconformity.
So do you think you've got a greater grasp of geological time?
Yes, I think we do.
I agree, yeah. So we established 3 mountain building periods in Caithness.
Yeah, I've definitely got a better handle on how quickly the Earth's surface changes.
I think the boognometer helps us a lot. So let's take a look. So I've gathered together on the boognometer all of the time arrows that we've collected on our journey, and it shows us many different hills and mountains, lots of different locations, and critically also it shows us different periods of time. So we've got these rates of geological change, and when I sorted them into geological processes, I found something really quite remarkable. It seems that most geological processes operate at about 1 kilo Bugnov.
Okay, so that's then 1 kilometre per million years, or 1 metre per 1,000 years, or I think, as is easiest for us to visualise, as 1 millimetre per year.
Yeah, and I think that gives us a kind of rule of thumb that will give us a much better handle when we have to think about geological time.
That's really useful.
Yeah, it does help.
So I actually found the timelines that we established in Caithness really quite useful.
Yeah, I wonder if we're missing something here. Tom, how tall is the cathedral again?
Oh, it's about 50 metres.
So say 46 for the purposes of this. And the Earth is 4.6 billion years old.
Mm-hmm.
So that would make 1 metre of the cathedral the same as 100 million years.
Katie, that's genius.
It's like our own wee Da Vinci Code.
Yeah. And who built Moslin Chapel? William Sinclair, Earl of Orkney. See, all roads lead back to Orkney.
Wow. So on our Da Vinci timeline, this is 100 million years, and the floor is the present day. Now, using that scale, the building of St Magnus Cathedral covers just 0.1 millimetres at the bottom of this pile. That's equivalent to the thickness of a human hair.
Wow.
And approximately here is the timing of the last uplift of the Scottish Highlands at about 50 million years ago. But if we go back to the Caledonian mountain building period, then we've got to go up to 5 metres. above our heads.
So that takes us to about the top of that first window there.
Yes.
So we have all that time on top of us.